Hello, everyone. Welcome to SAT Math Question of the Day with Professor Emeritus Seth Chaiken from University of Albany and his brother Joel Chaiken, where we try to help you understand how to do and, more importantly, how to approach SAT math questions. So here's our question of the day. I apologize for not being that clear, but it is readable. Website uses the formula above, and it gives you the variables. Which of the following expresses the number of favorable reviews in terms of other variables? So as soon as I see this, I say literals. A literal equation is what you did in algebra, where you solve for one variable in terms of the others. You sort of look at the answers. You realize that F equals, which means that we're going to be solving for F. In some ways, like all this stuff is sort of irrelevant. All they could have said was done this and say solve for F. That's the essence of the problem. I think it's useful when you do math problems in general to get right to the essence. And get to the essence as fast as possible. We're just solving for F. All this other stuff is actually just a waste of time to read.
Yeah, so the point is to notice that the question is asking for the number of favorable reviews, and that they told you that that is F. So it'd be a good idea to write the F here.
Yep.
And so the problem is, given the equation above, solve for F.
Solve for
Okay.
F. So then you write the equation. Now, this is algebra. We're solving an equation in algebra. Neatness counts. Okay, neatness counts. So you write R is equal to F. And it's helpful to, well, N plus F.
Yeah.
There are two ways.
Rewrite the equation carefully.
Yeah. There are two ways to do this. I'm going to do it one way, and I would not be surprised if Seth does it another way. Okay? Because I'm going to use the cheap and dirty way to do it. And Seth, being the professor that he is, was not going to do the cheap and dirty way. But I'm going to do the cheap and dirty way because I'm an engineer. So what I do is I put a 1 over here and I cross multiply. So I do R, but I love parentheses. My attitude is that the more parentheses you have, the better. Okay, and that's just F times 1. We'll just leave it as F. Now we distribute. Oh, thank you, Seth. This is Rn, neatness counts, plus Rf is equal to F. Now, this is a little harder than, like, most this is not that easy, actually, because you have to do factoring. You have to say Rn, you have to get the F's together. So you do
get them together
minus Rf. Okay, now you really got to get the F's together. So you factor out the F, and you get 1 minus R. Notice our goal is we're going after the F by itself. We really got to isolate this F. We're getting there. And then we divide by 1 minus R. You're allowed to divide by 1 minus R. And then we get F. So it's Rn. Now you got to really be careful because the 1 minus R and the R minus N can really screw you up. So these are the only two that have an Rn in the numerator, right? And notice how if you're dyslexic, you're in trouble. I'm dyslexic, so I may have a problem with this. And then it's this one. So, Seth, I suspect you're going to say cross multiply is not on the table. Like, how would you actually say?
Pretty much it's the same thing. Yeah.
Really?
Yeah.
Oh, cool. Really? You would cross multiply?
No, and of course another way of seeing to take this step is don't bother dividing R by 1. Simply multiply both sides by N plus F.
Right. That's the more legitimate way to do it. Right. If you multiply both sides.
Well, both are legitimate.
Cross multiply.
Another thing to do is to go like this. You could multiply by N plus F and divide by R, which amounts to swapping N plus F equals F over R. This is cool because it gets the F's kind of added together.
Right.
And then you could bring the F's together and you could do it differently. You'll come out with the same answer if you don't make a mistake.
The thing that's a little bit hard about this, the first time a problem like this is given when you, I'm sure, I hate to speak for people, but the first time generally people see this type of literal, they never get it right. They just totally, this one here, when you're in 8th or 9th grade and you see that, it's very hard to get that right the first time you see it. But now you're in almost 11th grade or in 11th grade, you're sort of expected to see that if you have this pattern, you need to factor out or sort of undistribute. I know, saying undistribute is horrible, right? Seth, what do you say? The word undistribute.
Sure, you can undistribute, yeah.
Undistribute, yeah. So you have to see.
Undistribute, it means factoring.
Yeah, it means
undistributing is a kind of factoring.
Yeah, so that's sort of the key to this problem. If you don't remember how to unfactor, not undistribute, or how to factor this F out, you're going to have a problem solving this equation.
All right.
Okay, that's it.
Okay.
Okay, great.
Well, we could talk about some crazy, we could look at an engineering approach.
Okay, so why don't we bid everyone goodbye? Because we don't want to torture them too much today. We don't want to torture you that much. But if you're interested in like the additional stuff that we have to say, please hang on and we'll bid our goodbye. Just please like us, dislike us, comments. Everything is welcome. We want all comments, instructive, destructive. We need comments so that we can make these videos better for you. Have a good day. And Seth, what do you want to talk about? I'm interested to hear what you have to say about this.
The data is this equation. And the problem is to find an explicit expression for R.
Okay.
Yuck. I moved the stupid red thing around. And the problem is to find an explicit expression for R. Okay.
Right.
So, well, whatever the expression is, it has to be true for particular values of F.
It has to be true for all values of F.
Or it has to be true for all values of F, and so it has to be true for any particular chosen value of F.
Absolutely right. Absolutely correct.
So you could pick values of F to test whether to test and eliminate some of the choices. So I saw we lost. Okay, so if F is 0, the equation says R equals 0.
If F is 0, R equals 0, right?
Or no, better. Yeah. So if F is 0, then R equals 0. So if R is 0. So when R is 0, we must have that F equals 0.
Right. That's right.
Okay. So which of these, check out each one. The bottom two, if R is 0, we get F is equal to N.
They don't work. It's obvious.
It'll work.
It's obvious.
It's no good.
Cross them out. Yeah.
And so that leaves us with only A and B. Now, the description of the function says that F is a number of favorable reviews, and the rating is a fraction. So if the rating is
how do you know the rating is a fraction? Oh, because R equals F.
Yeah. Okay, the rating is if F is the number of favorable reviews, N is the total number of reviews.
Yeah. Right. Yeah. Okay.
Therefore, R is a ratio of a positive or possibly zero number.
Yeah. It's like 5
to a larger or equal.
Yeah. No.
R is
we know it's a fraction.
Okay, and therefore, A is eliminated because if R is this fraction less than 1, the denominator is negative. So that's ridiculous. And
Oh
so
my
the only
God.
remaining answer is B.
That is like so smart.
Yeah.
Wow. I don't know how anyone's going to do it that way. That is really smart. You would realize that R is a fraction. R is a fraction.
Yeah.
That is really
And
clever.
and in fact, so what is given? Yeah, this is the equation that's given. F over n plus f
Yeah.
is the is when f n and R, when f and n are counting numbers, which the problem says,
Yeah, yeah, of course.
then R is a
Positive
it's
fraction.
a positive fraction.
Yeah, less than 1.
And it doesn't make sense in the problem if n equals 0.
Right.
F might be 0.
Yeah.
And so R is R might
Yeah,
be
I
0.
know.
R
Right. Yeah.
R could be 0, and it could be equal to 1.
Right. Right.
Yeah.
Right. Yeah, that's a really, really clever way to do it. I wonder whether the people who wrote the SAT even thought of anyone doing it that way. I mean, it's interesting. I don't know. That's really, really clever. Yeah. Wow, that was a really cool way of doing it. Yeah. Yeah. Very often.
Wait, could R be 1? Could R be 1?
No, it
can't be
0.
1. Yeah, R can't be 1.
Yeah. It's interesting because you did bring up a suggestion I do with oops, you erased the whole thing. It doesn't matter. We're basically done.
No, I'll undo it. Yeah.
This does bring up a quick a method I show, but nobody uses it. It's very impractical. But if you have some crazy equation like here, x squared plus 4 and x squared minus plus 6x plus 9, and then we do x minus 3, and we do x plus 2, and we have an x squared minus 9, right? Some crazy thing, right? And then the teacher tells you that this is, and no, and let's say you simplify it, right? You do all your simplifications, and you get x plus 4 divided by x plus 3. And you have no idea how to check this.
Yeah.
You could do what Seth did. If
Yeah.
this is obviously not true, I'm just really making this up. But if you wanted to check this and you have an infinite amount of time, you let x be 2. You test x equals 2. And then you put 2 in here and you get some monstrous thing. You put 2 in here and you get 6/5. And you see if you get it right. Now, on a test, this is completely impractical.
Well, it's even easier. The other choice to pick is x equals 0.
I would not do x equals 0 because you could make mistakes and it would still work out. I think x equals 0 is dangerous.
Well, x is no multiple of x. X is not a factor anywhere.
I don't know. Yeah, you could try x is 0 as a quick and dirty answer, right? I personally wouldn't stake my life on testing x equals 0, but x is 0 is a good way. Is really, really fast way to check. So I don't think what is
analogous to making x equals 0? You could take x to be infinity.
Oh, that's like getting into the calculus stuff about limits.
Yeah, that's getting into the calculus.
Yeah, we don't want to talk calculus.
And indeed, what you could see is that when x equals infinity, the numerator, is a fourth degree polynomial, and the denominator is also a fourth degree polynomial, and the highest order coefficient is 1 in the numerator, which is the coefficient of x squared times the other coefficient of the other x squared, which is 1. And the coefficient of x to the 4th is the coefficient of x times the coefficient of x times the coefficient of x squared, which is 1 times 1 times 1, which is also 1, which gives you coefficient x here, coefficient x there.
So anyway, that's really funny. That's really interesting. So in other words, you're saying that this is actually true, even though I made it up. Total nonsense. This is actually true when x is about like a million, billion, quadrillion, right?
Yeah.
What I just wrote is actually true if x is ridiculously large. Wow, that's pretty cool.
Yeah,
that's pretty cool. Again, I would.
The only values you need to stay away from, or or employ when you have more deeper knowledge of rational functions are the values that make the denominator zero. They have
Yeah,
to
yeah,
watch out
right, yeah.
x equals 3 or x equals minus 2 or x equals plus, what's that, x squared minus
Yeah,
9,
x squared minus
x
9.
equals plus or minus 3.
Yeah, right, 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 right.
Yeah,
Yeah.
yeah,
Okay, anyway, this is a nice way to check, except it's completely
yeah.
impractical. But if you're dying to get this, see if the answer's right, you can check it out. So anyway, so this is cool. We brought in a few extra things. I didn't realize that. Wow, look at that! I made up an answer that was right for x equal to infinity. Okay, I guess that's it.
Well, what happens is, this is a weird thing where uh, the left-hand side, some people would say the left-hand side makes no sense when x equals 3.
Okay.
But the right-hand side does make sense when x equals
Yeah,
3.
so it can't be right.
And that is, no, what happens is
Oh,
the
right.
expression on the left has what's called removable poles.
That's right. Yeah, removable holes.
Right, right.
Yeah, yeah.
And basically what happened, well, the idea is what happens is the x minus 3, as you could see, is a factor.
Yeah, let's cheat. Let's cheat. Let's put
Something's
let's
wrong.
yeah,
Actually,
yeah,
I
yeah.
don't
This
think
is
this is
something
right.
I made this up.
I
I
know,
made this
yeah,
up.
yeah, but it's not.
Let's
It's not.
change it.
I don't
Let's
think
make
it's
that
really.
an x plus
So,
4. Let's totally
and
cheat.
is
Let's make
x
that an x plus 4.
is
and
that
make
x
this an
squared
x
plus 4?
Yeah, yes, I'm changing
Yeah.
it. I'm
So
making it
x
an x
squared
minus
plus
3. There
4.
we go. See that
Yeah.
now we changed
This
the
thing here is x plus 3 squared.
Yeah.
Right.
I made this
And
up. Don't read too much into it.
yeah.
Don't read too much into it.
Yeah.
I made this
This is
up.
right. Yeah. This is
It's nonsense.
Yeah. Okay.
This is not. This was only to make the point of how to check something like this. It's not meant to actually do what we were talking about.
Well.
But I know what
yeah.
Seth's talking about,
It's
and you've done this in school.
Not
You've
equal.
seen this thing about the holes. If you have a factor here and a factor
Yeah.
here, they cross out, but then you have to write down x can't be 3. Like if you had to graph this, then you have to make sure to pay attention to the holes. That actually is done in 11th grade math. That's done in classic 11th grade math. That's done in Algebra 2. The classic Algebra 2 curriculum. The holes. Yeah. Everyone forgets the holes, but you can't forget the holes. Okay? We're okay?
Yeah.
Great.
I'm wondering if we should summarize, clearly what we're saying about this example.
Yeah. Fine. I totally agree. We can't leave people hanging.
Don't leave them.
We are not going to leave people hanging.
What did they talk about? What did they say? It's all confusing.
I'm under strict orders from my brother not to write in thick ink, even though I love to write in thick ink. So I'll tell you what, it'll be moderate. So how about this? X squared minus 9 divided by x plus 3. Okay? Fine.
Oh, okay.
And here you're supposed to graph this, okay? Here you're classic. This is
graphic, cool.
Y equals, right? Now we're talking about the
cool.
situation of the whole, where we can clearly describe what.
Cool.
Right. So first thing you do, Pavlovian response. When you see a polynomial, you factor it. By the way, we're not really talking SAT math anymore. We're really talking 11th grade math. Right? You have this, right? Pavlovian every time. Well, in SAT too. Anytime you see a factor, every time you see a polynomial, you almost always factor it. Just Pavlov, you just do it. And now in this case, you realize that, these two cross out. So this thing simplifies to x minus 3, which if you graph it, is minus 3. It looks like this. Right? That's the graph of y equals x minus 3. But then it says, well, I'll make the note, and then you can talk about it. But x can't be negative 3. So you put a hole there. X can't be negative 3. So that's the graph. And you have to leave a little hole. Is that right?
Yeah. So it's called a removable singularity because, you could extend it you could remove the condition that x is not equal to minus 3, and 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 a uh, 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 and use y equals x minus 3 as a function that has the same values on all of the x's except for minus 3,
Right.
and is continuous
Right.
at
so y is equal to x
at
minus 3,
at minus
and
3.
x and y is equal to 6.
Yeah.
When x is equal to 3,
Yeah.
and when x is not equal to 3.
Yeah.
Right?
Yeah.
Minus, is it 6 or minus 6? Wait, no. When x is 3, what did I do?
When,
Oh,
when
minus
x
3.
is
No, minus 3, minus 3,
yeah,
minus 3.
you get minus 6.
Minus 3.
Yeah.
This is a minus 3. Is that right? And then this is a minus 3. X. Right?
Yeah.
That's right.
Yeah.
Yeah. That's
Yeah.
why Seth said it's removable, because you could cheat, right? You could just say, hey, I control the situation. I'm going to force the function to be value negative 6 when x is minus 3 because I make the rules.
Yeah. Yeah. Now, if you change the 9 to an 8, what would happen is when x is near negative 3, then the function the value gets very large when you come in from one side going near negative 3, right, and gets very small, extremely negative and extremely positive near x equals minus 3.
That's called an asymptote, which we won't talk about.
And that's called, so it's asymptotic to a vertical line, and that's what's called a non-removable singularity. Yeah.
Yeah.
And it's called a pole.
Not much you could do with those.
Yeah.
Can't
but
cheat
when
with
those of you who go in to become electrical engineers or take some of the systems theory courses in mechanical engineering will learn all about poles.
Yeah, basically explosions.
Mm.
People like explosions. They like.
Well, the poles are, pole is a function. A function has a pole when it is something with let me erase what I did there.
I'm going to move it, Seth. Excuse me. Okay, there you go.
Is something divided by x minus p, and then we say p is a
right. So basically, you get behavior that is crazy, asymptotic, crazy, unpredictable.
Not too crazy.
No, crazy enough.
Yeah,
crazy.
It could be worse.
Certainly crazier than crazy.
Yeah,
okay.
Could be a lot worse.
So we have totally beat this problem like the pole to a pole. But it is, and we went into a little bit of 11th grade math. Okay, have a great day then. If you can, after this video, try to have a good day. Okay.
Okay.
Bye-bye.
Bye-bye.